Otherwise, hearing for me.
I watched so many. I never watched the
But
one.
it was like, I'm used to it. I see that. That paper cut.
I love basketball. I would like to buy.
All right, let's go ahead and start in here today. We want to finish up the optimization. Well, not finish up, but we will continue to have some of the optimization problems on homework, so we continue to practice those. But there's really nothing new to add to the optimization idea. Okay, I mean it's these steps here essentially. We want to identify what we're trying to find the max and min of. Write and label an equation with that. And the key thing, and then the new thing that we learned today is sometimes confused with the steps we have here. Because in the new thing we learned, we're also going to kind of have some steps that we follow. Now again, I'm not a fan of memorizing, do this step, then do this step, then do that. If that can help you, that's fine. But you really have to understand the overall concept of what you're trying to do. That's really how you're going to determine what to do next and what steps you need to go through. Okay, so that's the really important thing. Otherwise, you're going to confuse the two different types of things we're doing. They're not anything alike, except the fact they have a derivative in them. But otherwise, they're not anything alike. So there's no reason we should confuse steps unless we're just trying to memorize things without understanding. And that's not good in any situation here. Okay? So what we're trying to do is maximize a quantity. We need an equation for that quantity. We need it to be in terms of one variable. There is a method where we could do it with some implicit differentiation, but that really confuses things because in the new thing we do today, we definitely will be using implicit differentiation all the time. And so I like to avoid it in these, just that's one other place people could confuse. So we try to get it, step 3, very key here, try to get it in terms of one variable. Then we do the derivative with respect to that variable. So x or whatever, r, whatever it happens to be. And then we look where we're supposed to look for maxes and mins, which is at endpoints where the derivative is 0, where the derivative is undefined. And then we answer the question that's asked. Now, we might do a list of candidates, we might do a number line, and we've talked about those situations. And a lot of the problems, the story type problems, real life type problems, you can sometimes do a number line. Sometimes there's only one possibility, one candidate, and the others are like infinity and that kind of thing. And so you can use that as opposed to your list of candidates. So it depends on the problem, depends what you prefer and those things. And we've talked about that over the last couple of days. So, I tell you what, let's look at the business packet first. On the website, I think I mentioned this, that I did put the answers. Did I tell you that? I think I did say that yesterday. I do have these worked out just by hand, but they're somewhat incomplete solutions. I mean, on some of them I tried as I was working them, I tried to maybe do a list of candidates or try to have the justification, but you should not treat these as full, complete solutions. If mine looks like this, that'll be perfect. That's probably not the case. These are here more for you to help, hey, this is how a good way to set it up. This would be a good way, this is what the derivative would look like. Here's what the final answer should be, but not necessarily complete when it comes to the justification and those kind of things, right? So understand that. But this was a pretty straightforward revenue function, was just given to you. They didn't tell you what context it was, what things we were making, what the units were. That's our revenue. Here's our derivative, one stationary point, and that turns out to be the max. And again, I didn't do I didn't do a number line or anything, which should be. Somehow there should be a number. This would be a good one for a number line, really. I suppose you could say, well, 0 would be the littlest x could be. There really wouldn't be a biggest for x. Somebody in the other class said they used infinity. And I said, that's fine. But if you're going to do a list of candidates and you're going to justify that this is a max, do not do r of infinity. That's not good mathematics. Infinity is not a number. You should say instead that as x approaches infinity, if you want to talk about that, then the R goes towards negative infinity, because that's what would happen. As x gets really big, this is going to get really big, and it's negative, and so that's not going to be a max. So if you want to do list of candidates, but this would probably be one that really work well for a number line. And remember, if you do a number line, then there should be some discussion about, okay, if this would be your number line, okay, like this. Is that right? Did I do that right? Or is this maximum? This is maximum, yeah. So it's the other way around. Yeah. So when you do that, so if you've got this number line, then there should be a discussion. Anytime there's a number line, there should be a discussion of it. And this would be, use the word always, right? That R prime is always positive before 200, so R is always increasing. And after, R prime is always negative, so R is always decreasing. Therefore, 200 units would create the max revenue. Okay, that kind of thing. So, and then 8, so that was a pretty easy one as far as that goes. Now, in 8, it was average cost per unit. So you needed to take the cost equation they gave you and divide it by X. Right? This is the cost in dollars, and then divide by number of units, cost per unit. So I went ahead and just worked out the derivative. So what I did is I split it up first. I split it up and gave it this. You wouldn't have to do that if you were using your calculator to do it. Most of these problems in the book and in the packet are meant to be done without a calculator. That's how they were written. Okay? At least without a graphing calculator that'll do the derivative for you, like we have. Okay? But I'm telling you, I'm going to go ahead and let you do that on these. So this is what C bar would look like if I simplify it a little bit. Then I could do my derivative, and then I use the calculator to solve it at that point. Okay, now, let's talk about this a little bit. Our candidates are when C bar prime is 0, which was there. Also when C bar prime is undefined. Well, it's undefined when X is 0. But it turns out that if I try to plug that back into my original, it's also undefined, right? So I can't really use 0 in my list of candidates because I don't get an answer out. Okay? So 0 wouldn't really be an endpoint there either. So again, this might be a good one for a number line kind of situation. Okay, and this one would go negative to positive, I believe, because this one's a minimum. Okay, so it'd be the same kind of reasoning as the other. Okay? All right, any in the book that you wanted to talk about? I want to talk about 21 for sure. I want to talk about 21, but 27?
27.
Okay. So let's do 27 first. So on 27, we're talking about the rectangular box situation again. Okay, kind of like we were in the one yesterday in 28B. So we have a rectangular box with a square base. All right, and I think it did say square base, right?
Yes.
So we know this is X, and we could call this Y. All right, so we have the, like so. And then it asked, there were two parts. One was volume, one was surface area. Do we do surface area? Let's do that. Yeah, it's really a formula you should know. I mean, what is surface area? Just in general, what is surface area? The area of all the faces around the outside. It's just the area around the outside. So what's the area of this one up here? X squared, right? The area of this is X squared. So there's two of those. 2X squared. What's the area of this face on the side here? XY. How many of those are?
4.
There's 4 like that. So we add those together. So that's just surface area. It's the area of the side. And so, surface area is just going to have circles or maybe the tough one would be a cylinder, and I would probably give you that. That's a little tougher one to get surface area. But anyway, so there's what we're trying to maximize or minimize. Okay. And the volume would just be X squared times Y, just like we did in 28. So that's why I didn't pick that, because that's very similar to what we did in 28. And then what else? So we have two variables, so we'd like to get that Y out of there. So what did they tell us? We had 100 centimeters of wire. Okay, well, each piece here is a piece of wire. So that's 1, 2, 3, 4 X's, 5, 6, 7, 8 x's. So 8x plus, and here's a piece of wire. It's y, and there's 4 of those. So 8x plus 4y would have to equal 100. That would be right. Okay. So there we go. So this would be our information that we want, and so we could do this, and we could divide by 4, and we get 25 minus 2x, that kind of thing. I could substitute that in for y. So I get a equals 2x squared plus 4x times 25 minus 2x. And you can use your calculators at some point along the way here. It's probably necessary. 100x minus 8x squared. So in the end, our area equation is negative 6x squared plus 100x. Is that right? So now we're looking for our list of candidates. So negative, one of our candidates is when the derivative is 0. That derivative is never undefined. So what's 100 divided by 12? 8 and 1/3. So now we could talk about endpoints. The littlest x could be, if you want to go that route, the littlest x would be 0. What's the biggest x could be? The biggest x could be, I guess you could say, would be if you used all the wire for x, right? If y was 0. So 100 divided by 8, 12.5. So I suppose you could make the argument that the biggest x would be. Now clearly that's not really going to make a figure. There would be no y, so there would be no faces, and so there would be no surface area, and that's clearly not going to be. Was this a maximum problem? The largest surface area? Right? So we're looking for a maximum. So you could do your list of candidates now. You could do A of 0, and you could do A of 12.5, and you could do A of 8 1/3, or you could do a number line. This might be another good one for a number line, and it is going to be 8 1/3 is going to be your largest, whatever that comes out to be. When you put it back into A, and when you plug that back in here to figure out what Y is, what do you get? Also 8 1/3, or not? It would be, right? So it's a cube. So the maximum ends up, and I can't remember, what did this question ask for? Dimension. So it'd be 8 1/3 by 8 1/3 by 8 1/3. It's a cube. Okay? Not surprising. Maybe in that case. All right? So those would be your answers there. Okay? So fairly straightforward on that. Now, 21. The thing I like about 21, maybe it's because I'm a coach and it reminds me of problems. When I was in college, and I was a math major, obviously math education, and so I took a number of, I took abstract algebra and advanced calculus and differential equations. The 2 hardest classes I took in college were for my coaching endorsement. And you don't even need a coaching endorsement to coach. I mean, if you're a warm body and say, I'll coach, and I'll say, okay, there you go, basically. But, I mean, because they're always looking for people to help coach. And so, but I don't know, I didn't know, I'm 19, I did a coaching endorsement. Then they'll really want to hire me because I'm this coaching endorsement. So they had a coaching endorsement, so there were several classes you had to take. Well, 2 of the classes I had to take for this coach. You'd think it'd be really easy, right? And trust me, like coaching basketball and those were really easy. But 2 of them, one was anatomy. I had to take anatomy. And not just not anatomy for coaches. I had to take the same anatomy that the pre-med majors had to take. This was at UNL over on East Campus in the big laboratory with real cadavers. With the professor that was the creepiest. Now, it turned out later, really nice guy, really great guy. I asked Mr. Limbach about our anatomy teacher, Dr. Johnson, at UNL. He had an eye condition, so he had to wear dark sunglasses even indoors. So I never saw him without these dark sunglasses on where you couldn't see his eyes. And he was in the room with the cadavers, and it was just the whole thing. It was just crazy. And this was a class that the pre-med students usually took twice because they needed it for their GPA, and most people did not get above a C the first time they took it. It was crazy.
What did you get the first time? I like that face.
I squeaked by with a D plus, and I said I'm good enough, okay? Because it was just for my coaching endorsement. That's all I need. Now I did not put in quite the amount of time that I should have. I think I could have got a C, but anyway, I could have got a C.
That makes me
It was-
want to go to college.
It was tough, really tough. And then, so the second hardest one was biomechanics for coaches, which was basically a physics, basically a physics and studying the different physics laws that affect athletic competition. So like for a discus thrower, shot putter, long jumper, as a track coach, I think of those kind of things. This example in 19 was a football going, but all those different things that you needed to know, which that I found fairly interesting, but it was really hard. I mean, it seemed harder in some of my math classes. It was a 1 credit hour class too. I met once a week. It was like, gosh, I'm doing a lot of work for this 1 credit hour. So this problem reminds me of that. So what they did in 21A, they said take the equation for 19, okay? And what was that equation? It was y equals 2v sub 0 squared.
It's gravity times m over n, 1 plus m squared.
Okay, that's the one. I'm sorry, that's the one
sorry.
for 21. I'm sorry, I wanted the one for part B.
I have that one.
Yeah. Or for 19. What
For
was the
19?
equation of 19?
Y
Equals
mx
mx
minus g over
2v sub 0 squared.
times 1 plus m squared times x squared.
And then squared.
And x times
X squared. Oh, that's right.
No. 1 plus m squared
I
times
know.
x
Yeah, I know. So this is an m squared in here. And then
No, you
times
gotta do-
x, and there's no squared on this. Okay. All right. So now, understand in 19 what everything stood for. G was gravity, V was the initial velocity that the football was thrown at, M is the slope or the angle that it was thrown at, X is the horizontal distance of the object, and Y is the vertical distance of the object. So, okay, so that was for 19. But in 21, what they want to do is they want to rearrange that to make an equation for the horizontal distance, which is X in this one. So what they're trying to do is get X by itself here. Okay, trying to get X by itself. Now, the horizontal distance that the object travels is going to be when it's back on the ground. Now, what's true when it's back on the ground? Y is 0. So what they do is they take this equation, put a 0 for Y, and they solve it for X. Okay, so we put a 0 here, and we solve this for X. Well, you could factor out an X, and you would have this whole thing. So this is part A of 21. Okay, so we factor out an X from this, and then we factor out an X from this, and we get 1 plus m squared times X, like that. Okay, so X is either equal to 0. Well, that makes sense. When's it on the ground? Well, it's on the ground at the beginning, right? And then it's on the ground again out over here. Okay, so when X is 0 or when this is 0. So if we set this part equal to 0, I could add this over to the other side, so I'd have m by itself, and then I have this over there, so that would be g over 2v sub 0 squared times 1 plus m squared x. So now to solve for x, I would divide the 1 plus m squared over here, right? What's that? This x. What I'm doing is I got x times all this equals 0, so either x equals 0 or this equals 0. Yeah, so the x equals 0 is at the beginning, so I don't care about that. And so now I just care about this one, what this x is, and that's going to be this. Okay? So now I divide by the 1 plus m squared, so that's over there. And then to get rid of this, I can multiply by the reciprocal, right? And so I'd have this 2v sub 0 squared over g, right? And so that equals x. So that's where that equation comes from. So that's what 21a was. Saying, all right, when it's back on the ground, when the y is 0, okay, this is what x will be. So this, and then they relabel that R, big R. Okay, so big R is the range. All right, so That's where we're at now in 21B. Now, V sub 0 is just a constant. That's the velocity the ball's thrown. Gravity is a constant. So the variable is the slope now. So what we're going to do is we're going to say, all right, how can we maximize the distance of this object? And let's use a shot put, for example, okay, being a track guy. So let's use a shot put. So if I throw the shot put, I want to get the maximum distance. I want R to be a maximum. At what angle should I throw it to get that maximum? Right? That's what this problem now is. Right? So this was what we learned in this class. As a coach, you want to teach this sort of thing. Now, does Kitzelman tell you an angle to throw the shot put? Does he ever?
45-ish.
Ish. Okay. And I've asked different, athletes, what do they say? What is now the guys this morning, they were saying Coach Larson would say like 42, 41, 42, 43, somewhere in there. Okay? So, here's the thing. The reason that the coaches don't make a huge deal about that angle, if these are the things that affect the distance, let's investigate. One is gravity. Well, you're not going to change that. And the shot put's not really going to be affected by it much anyway. Right? I mean, it's air resistance, those kind. Well, I mean, it's affected by it, but it's not going to change. There's nothing you can do to that. What's this one? Initial velocity, the velocity you throw it with. What's going to determine that? How strong you are. What else? Your speed and quickness, your technique, all those things. That's what you work on, right? This is going to have way more effect probably than the angle. Now, obviously, you don't want to do that. That's not good. You want to throw it straight up in the air, right? I mean, so common sense is pretty much 45 degrees. I mean, that's just kind of common sense. But what will determine mostly is this initial velocity. So the coach is going to spend most of his time getting you to improve that velocity, your speed across the ring, your strength, get in the weight room, your quickness, your technique. Those are the things you work on. Part of the technique, though, would be this angle. Now, if you take, though, an Olympic caliber athlete, okay, all those guys and maybe gals who are at the very peak of the sport and all steroided up and everything, and they've maxed. Maybe not. That's right. It's against the rule. But they've peaked out on strength. They've peaked out on technique. Quite honestly, they're probably about as good as and that's where the really intense video analysis and those kind of things will come in. And now a degree or two here, that may make the difference between those few inches needed to really separate you at the top. So it could become important at that point. So it's not a huge deal probably at the high school level. A lot of other things you can spend your time working on. But it's interesting to find. So that's what we want to do. We're going to maximize this. Now, how do you put this in your calculator? Well, quite honestly, I don't think you need to. It's really pretty simple without it. This stuff here is what? That's just constant. That's a constant in front of the function. When we do a derivative, it just hangs out anyway. So we're not going to do anything with that, and we're going to do a quotient rule on this. Now we're doing the derivative with respect to m. To do the derivative top, that's 1. We leave the top or the bottom alone, minus the top left alone, times the derivative of the bottom, which would be 2m, all over the bottom squared. So there's our derivative, and then we're going to set that equal to 0. Well, this is not going to be 0. With that part we can just ignore for the time being. That won't be 0. So when is this 0? Well, it's 0 whenever the top is 0. So what's the top? Well, it's 1 plus m squared minus 2m squared, which is 1 minus m squared, which is when m is what? Plus or minus 1. Now, you're not going to have a slope of -1. That'd be the situation where you throw it down into the ground, right? So that's not going to maximize your distance. So really, the only viable candidate is m equals 1. Now, that's slope we're talking about. So what's a slope of 1? That's 45 degrees, right? Slope of 1 would be 45 degrees. Okay, so according to this formula, the answer is 45 degrees. Should be the slope that you throw this with. Now, why would Coach Larson tell them 42 degrees then and not 45 degrees? Because he never took calculus. I actually, the first time I did this, I went down and talked about it. He didn't know all the math behind it, but it was funny because he pulled out some articles and some things that showed, and it had some math and some graphs and stuff, and he showed me several things that talked about around 42 degrees or something like that is what he was basing that on, where that came from. Well, look at the picture here. See, the hint, my hint to you is here's the picture of the situation we were just doing. And this says that the optimum angle to throw it here would be a slope of 45 degrees. Why is that different than throwing a shot put? Where is that one being thrown from? The ground, right? You don't throw it from the ground. You throw it from maybe 5, 6, 7 feet high. So you throw it more from in here. So if this is the optimum trajectory to get the most distance, you're actually throwing it from here. What would the tangent line look like there compared to back here? Not quite as steep, right? It's going to be steeper here, and it's going to be getting less steep. So when you throw it here, it's going to be less than 45 degrees. Now, the taller you are then, the less steep you should throw it. Now, how much steep, that would be another calculation you probably have to go. You probably have to go back and change this original equation a little bit if we're not throwing it from the ground. And then that would change this one, and then you could maybe find that. But again, there are a lot more things more important, in achieving that than just this angle, so it's probably not worth all that effort. But from a mathematical standpoint, we can see why that would be. So the taller you are, you might throw it a little flat. Shorter you are, you might get more towards that 45 degree mark. Okay? Is what you can learn from here. Now, if you're a long jumper, now there you do go from the ground to the ground. So now 45 degrees would be your optimum angle that you would want to take off, or triple jumper, or whatever. Okay, you'd want to try to hit that 45 degree. All right, you get too high, you're not going to go as far. Too low, you're going to hit too quickly. So that 45 degrees would be it. So that's kind of what's going on with number 21. Okay, again, I didn't do the justification. Again, this is one of those things. It's probably a one candidate thing. Could be kind of a number line situation. Again, what is it? It's essentially an upside down parabola. So those are pretty easy to find out maximum on those. All right. Why don't you go ahead and get your notes out now. We'll kind of leave that on the optimization end of things. You'll continue to have some problems. We'll do some more in the business packet. We'll have another packet here probably tomorrow that'll have some of the new thing we learned plus some more of this optimization. So we'll continue to go back through this. And then, of course, towards the end of the week, we have to review our parametrics and stuff. That's probably Thursday. We'll get reviewing those things. I don't know that we'll be ready to go for a quiz on Friday, so it's looking more like Monday. Okay, it's looking more like Monday. So we may throw in some midterm review in there one of those days a little bit. Maybe some of that's part of Friday possibly, which would be time well spent also. Here's what we're going to talk about then. The new thing here is going to be this idea called related rates. Related rates. This is section 4.5. Section 4.5. So we did parametrics in 4.4. We did optimization in section 4.3, and now related rates in 4.5. Now, again, these are story problem type situations as well. They use a derivative, but in a different way. There's going to be an implicit differentiation component to this. And it doesn't have anything to do with max and mins. It's all about rates, just like the title suggests. So you should not confuse these types of problems. I mean, the optimization are problems where they're asking for the largest or the greatest or the least or the minimum. These are problems that are asking about how fast something is changing. They're about movement and motion and rates. Okay, so they're just very, very different kinds of problems. All right, now this worked pretty well this morning. This is some new stuff I found that really leads us into it, which I think is going to be helpful. Something I haven't done before. So what we're going to do is we're going to build into this a little bit, up into doing a full problem of these. So the first thing I want us to investigate here is let's write these statements mathematically. John is growing at a rate of 3 inches per year. Now, I don't know if you write down this stuff. Maybe you just try to follow with me, and I'll show you when you might want to write something down. John is growing at the rate of 3 inches per year. How can I write that mathematically? J, you want to use J? We'll use J, that's fine. No? Anybody else want to add to what he said? He's right so far with the J. No? There we go. J, now wait, J, did I hear plus? Prime, that's what I was looking for. J prime. Why J prime? Because it's a rate. It's the rate of change of John. Okay, now some people might do H prime here for height or something, but J would be okay. Equals what? 3. There you go. No, would it be positive or negative 3? Because he's growing. So his height is in, think of the chart, his height is increasing. J is increasing. So J prime has to be positive. If J was decreasing, like maybe I'm 50, I'm probably shrinking. So mine would be a negative, right? I'll probably start to shrink a little. Seem to be. So J prime, then in that case, that'd be negative, right? So, all right. How about this? My mutual fund is shrinking by 4 cents a day. F prime 4 if you wanted to do cents. If you want to do it in dollars, maybe that. Okay. The radius of a circle is increasing by 4 feet per hour. R prime positive 4. Okay, the volume of a cone is decreasing by 2 cubic inches per second. I would say we'd usually use V there. V prime. And here's why we would use V prime and not C there. Because we'd be talking about the volume of the cone, we'd be talking about the height of the cone, the radius of the cone, right? And so C might not be specific enough of what part of it. So V prime equals -2. So that is one of the first steps in these problems we have to do is identify the different quantities that are in the problem and notice they're all rates. So it's going to be very easy to identify that we're doing a rate problem because you're going to have all these rate things going on in there. And we're going to label them as such. Now remember, this would actually be DJ dt. This would be like df dt. This would be dr dt. These are all with respect to t. dv dt. So a lot of times in these problems you see them written with Leibniz notation. Very important idea because in optimization, it's not that way. In optimization, when we had the volume that we were trying to maximize, we had volume and then we had x's. We were doing dv dx. We were doing the derivative of the volume with respect to the input variable. That's why we had to get the equation in one variable. So we could do the derivative with respect to that variable. We didn't have any x primes in these problems, in the optimization, but in these problems, we are going to have j primes, r primes, h primes, v primes, c primes. We're going to have it all over the place because we're doing implicit differentiation. Everything's with respect to time. Look at years, hours, days, seconds. Everything is rates with respect to time when we do these related rate problems. So they're all implicit differentiation. Okay, here's the beginnings of a problem like what we'll be seeing. I have a rectangle that's 10 inches by 6 inches whose sides are changing. Write formulas for both the perimeter and the area and how fast each is changing in terms of L and W. So, let's imagine a rectangle. Okay, as a matter of fact, well, let's do this first. So let's imagine a rectangle, length and width. What's the formula for perimeter? P equals 2L, bless you, plus 2W. That's the perimeter of a rectangle. Now, how would we write the rate of change of the perimeter of the rectangle? P prime equals, we got to do the derivative of this. 2, no, L prime plus W prime. Because remember, this P prime is not with respect to L and not with respect to W, and you're right. If in the other problems we were wanting to do the minimum perimeter or whatever, we would have to get this in terms of one variable. Not in these problems. We're talking about how, because think about it. It's kind of this situation here. Let me go to this. Here's what we're talking about. I've got a rectangle. Okay, here's a rectangle like so. As I drag this, look what's happening to the length and the width. They are changing. They are both increasing. What's the perimeter doing? It's also increasing. So as I drag this, the length is increasing at a certain rate, the width is increasing at a certain rate, and the perimeter would be increasing at a certain rate. I've got three different rates going on. P prime, L prime, and W prime. They're all different rates. Now, they could both be increasing, which is in this case. In this case, one is increasing, but the other is decreasing, right? Or in this case, the height is increasing, but the width here is decreasing. That kind of thing, right? And the area, not only that, but the area is changing as I do that. All right? So that's the kind of thing that we're talking about here. I don't know what just happened. All right. So now what is the area of that rectangle? Length times width. What's the change in area? A prime equals
L prime W plus.
oh, well, now we're doing a product rule, right? It's not L prime W prime. It's L prime W.
Plus L W prime.
Thank you. Very good, student. All right. So A prime, let's all line up single file. Okay. A prime equals L prime W plus L W prime. Right? Okay, now let's take this one step farther. What would a problem be like? A problem would be, a whole problem would be this way. It would say, okay, we've got a rectangle whose sides are changing. When the triangle is 10 inches by 6 inches, let me back up. We have rectangle. We have a rectangle whose sides are changing. The length and width are both, let's do this one right here. The length and width are both increasing at the rate of 2 inches per second. How fast is the perimeter changing when the triangle is 10 inches by 6 inches? That would be the problem. Okay? Now, some of this we've already identified, right? So the change in perimeter we already know is this equation right here. So that's going to come down to there. So how fast is the perimeter changing? Well, so we would come in here and in place of the L prime we would put what? Right? L prime, they tell me right here, is 2 inches per second. Right? That's at length and width are increasing at the rate of 2 inches per second. That's L prime and W prime. So I'm going to go 2 times 2 plus 2 times W prime, which is also 2. That's going to add up to 8. And what are the units going to be? Inches per second. Now, it's important that you're going to put your units on there. And there's two ways you know it's inches per second. Number one, it's perimeter, so it's got to be measured in inches. The other way you know is what the units were in the problem. Now, I know in physics, a lot of times in science class, they make you put your units as you go through the problem. I'm not going to make you do that. They should come out the same if you do it right, and you should just know what they should be. But right here, this 2 is in inches per second, and this 2 is in inches per second. So this would be 4 inches per second plus 4 inches per second. That's 8 inches per second. What about the area? That should be inches squared per second, right? Well, here's our A prime equation right here. So our change in area in this problem would be L prime, which we just said was 2, times W. What's W? That's the 6 from up here, right? When the length is 10 and the width is 6, how fast is the area changing? All right? And then plus, L would be 10 and W prime 2. So this is 12 plus 20. This would be 32 square inches per second. Now again, we know those should be the units because it's area, but we also know that the 2 was in inches per second and the 6 was in inches. So inches per second times inches should be inches squared per second. All right? That's the kind of problems we're going to be doing. How fast is this thing changing if these other things are changing at these rates, and how are they related? Okay, now in this one, they're decreasing. So what do we got? -2. The L prime and the W prime would be negative when we plug them in. That's the only difference. Okay? And then they go on to do some examples. We won't do these, but there they say, now what if the length was increasing at 3, but the width was decreasing at 3? Well, what did they just tell you there? Length increasing at 3 would be what? But what would we label it? L prime would be 3. And the width is decreasing at 3.
W prime equals -3.
W prime equals -3. And so a lot of, in these problems, we'll want to write that stuff down, and then we'll be plugging that in later on in the problem. At some point in the problem, we'll be plugging those values. But you can see why we need to be able to label correctly and understand these rates and their primes. When they're rates, they're primes. Okay. So then they do an example of a right triangle situation where the sides are changing and so forth. And a cylinder where the dimensions are changing, and so you got surface area and volume and stuff. Okay. Now here's kind of the strategy. Now I don't want you to write this down at this point yet. I'd rather you just understand the whole process, and then tomorrow maybe we'll copy this down and parts of this down if we want to. This is pretty close to the way I would do it. There's a few things I'd change here, but it says to solve related rate problems, you need a strategy. Related rate problems can always be recognized by the words increasing, decreasing, growing, shrinking, changing, and so forth. Make a sketch, I agree with that. Label the sides in terms of variables, even if you are given the actual values of the variables. Now, here's what they're saying there. I don't totally agree with that, but one of the problems we're going to do is going to be a ladder falling down a wall. Okay? So if I've got a ladder, so here's a wall, and I've got this ladder leaning up against the wall. Okay? Now, it's falling. So in other words, this is scooting out, and this end is coming down the wall. Right? So, according to them, you would label all sides in terms of variables, even if you were given the actual values of the variables. So in other words, I might tell you this is a 6-foot ladder. What they would say is you should label this X, Y, and Z, even though we were given that Z was 6. Now, in the problem, we'd also be given this. It probably would say something like this. The ladder is sliding down the wall. Probably tell you how fast it's being pulled. And I don't know why I labeled those X and Y like that. It seems to get backwards, doesn't it? Would this be X? Probably this be Y. But anyway, that doesn't matter. But so I might tell you how fast the bottom of the ladder is sliding out. Okay? And then I might say when the ladder is 5 feet down the wall, okay, how fast is the top of the ladder sliding? Or something like that. Okay, that might be the question. Well, if they tell me that they want to know when the ladder is 5 feet down the wall, that'd be Y. But it would be wrong to plug a Y into that, or a 5 into that. Okay, right now. The ladder is 6 feet tall. According to them, they would not plug it in there. I say it's okay to plug it in there. Now, what's the difference? It's not changing, right? That is not going to change ever in the problem. Now, let's read a little bit more about what they say here. It says, you will make a table of variables. I'm not going to have you do this. This is where they want you to make a table of the variables in the problem. There'll be 2 types. Variables that are constants. That's kind of an oxymoron, like jumbo shrimp. Variables that are constants.
Well, there are shrimp that are bigger than
Yeah, I know. And there are and we do that in problems. We say K is a constant. Well, we always think of letters as variables, right? So, but if it's constant, it doesn't vary, so it's not a variable. But what the point they're making is anything that's constant and will stay constant throughout the movement in the problem, to me, that's okay to go ahead and put into your diagram, put in right away in the problem, if it's never going to change. But any variables that are changing, those are special. And those we don't put in until the very end. So it's very important we understand that. All right, so 6 in this problem is never going to change. That ladder is always 6 feet tall, but the Y and the X are both changing, so I cannot plug those in. Okay, so that's going to be a key part of this. All right, then the 4th step says, or the 3rd step says, find an equation that ties your variables together. What would tie these together? What equation? Pythagorean theorem, right? X squared plus y squared equals 36. That's the equation I would work with here. The one we did in the last problem was an area or a perimeter equation, okay? So we have those. It says right here, you might need an area equation, you might need Pythagorean theorem, you might need a trig equation. One of the things I could have asked, as this thing slides down, this angle is going to change. Might have asked how fast is that angle changing? Okay, so we might need a theta in there, so we could have done a SOHCAHTOA kind of a thing. All right, so now it says you can plug in any variable in the constant column. Never plug in a variable that's in the changing column. So that's what I'm saying. We can go ahead and plug in the constants, I think, right away. Then we do the derivative with respect to time, t, implicit differentiation. So you're going to have x primes and y primes and h primes and r primes all over the place. Then we can plug in the rest of the variables. Then we can put the 5 in for the y, and so forth, and so on. And then you finish out. Okay, so those are the steps. So let's take example 5 here. An oil tanker spills oil that spreads in a circular pattern whose radius increases at the rate of 50 feet per minute. How fast are both the circumference and the area? Well, let's just do one of those. There's too much going on here. How fast thank you. How fast is the area of the spill increasing when the radius of the spill is 50 feet? That's a typical problem of this type we're talking about. An oil tanker spills oil, spreads in a circular pattern. The radius is increasing at 50 feet per minute. How fast is the area increasing when the radius of the spill is 50 feet? So, where do we start? Draw a picture. I'm not sure it's critical in this problem, but, you know, I think it's good to start with a picture. Okay? What's next? Area. So area equals pi r squared. Is there anything constant in this problem that I could plug in now? No, right? Everything's changing as this circle gets bigger and bigger and bigger. Now, the order you do all this stuff doesn't really matter. A lot of times what I like to do is write down the very first thing we learned when we were going through this worksheet here. Very first thing we learned was identify these different things. What does this 50 up here mean? How would I label this 50? That's r prime. Now, is that positive or negative 50? Positive 50, because the radius is increasing at 50 feet per minute. That's a prime. Okay, what is this 50? That's plain old r. Okay, those are two different things, right? I guess I should have done 20 maybe. All right, so these are values I'm going to plug in at some point. And then the other thing I like to do is write down what it is I'm supposed to be finding. What am I supposed to be finding here? What do I call that? So I'm trying to find a prime. So here we go. We want to find a prime. So now we're ready to differentiate this. So what's this derivative? Okay, let's write the a prime first. But yeah, a prime equals 2 pi r prime, right? Now, in an optimization problem, we didn't tack on an r prime, right? Because we were doing something totally different. We were finding the maximum of this function. And so we were doing the derivative with respect to r. We were trying to find when its slope was 0. And so what r value made a slope of 0. So we were looking for a prime with respect to r. So we would not have tacked on an r prime, right? Because r prime would have been 1. R prime would have been dr over dr. Just been 1. But we're not doing that here. We're talking about with respect to time, feet per minute, square feet per minute. So we're talking about dA dt, and we're talking about dr dt. So it's a different scenario. We're doing two totally different things there. Don't confuse them. We're not setting this equal to 0 or anything like that. We're plugging in value. Okay? So what do we know? Well, our values are all right over there, so this is a pretty easy one. We put in a 50 for R. We put in a 50 for R prime. Now remember, this is 50 feet, and this is 50 feet per second per minute. So that should be square feet per minute, which is what area is. So sure enough, this is comes out to what, 5,000 pi square feet per minute. And that's about as simple as one gets right there. Okay, I mean, that's just, everything's very straightforward. You got A equals pi r squared. Your derivative's easy. The things they gave you were easy. You plug them in, and away we go. Okay? Now, let's go through a couple that get a little more difficult, that add a little bit more to it. Okay? Number 6 here. A 13-foot ladder leans against a vertical wall. If the lower end of the ladder is pulled away at the rate of 2 feet per second, how fast is the top of the ladder coming down the wall at the instant the top is 12 feet above the ground? Let's just do that. Let's don't do part B. Okay, you guys do that. Put that, draw it up in your paper. See if you can get it set up. I kind of have it partially set up for you over there on the board anyway. Talk with each other if you want to. Or totally ignore each other if you prefer. Uh-huh. Uh-huh. All right, I'm going to uncover this. Don't look if you don't want to see it yet. All right, now I've left one of those blank the x. Everybody see why x prime is 2? And it's not negative, right? Because x is increasing. Again, that's the key. Think of the chart. As I pull that ladder out there, this x length here is increasing. So x prime would have to be positive. If I was pushing the ladder back towards the wall, then x would be decreasing. So x prime would be negative. But what's, and y, they say when the top is 12 feet above the ground, that'd be y. So how do I find x? I have to put the 12 back into this equation right here. When the ladder top is 12 feet high, then this would be what? 5? Yeah, so I'd put the 12 into the y to find x. So this would be 5 right here. So sometimes you have that extra, some information you need to get based on what they're giving you. And then y prime is what I'm looking for, right? So I have nothing to plug in for y prime because that's what I'm trying to find. So at this point now it's just some algebra. So I've got 20, I subtract that over to the other side. This would be 24 y prime equals negative 20. So y prime would equal negative 5, 6, or whatever that would be as a decimal. And that would be feet per second. Did you do that right? 5, 6? Okay. And we could give it 3 decimal places if we wanted. All right. So that takes it to a little bit higher level of difficulty, just a little bit more information to plug in. We had to find that x and do that. All right. And for fun, we can look at that. Look at that. Not if you've ever fallen off a ladder. It's probably not that much fun.
No, keep going.
Okay, do it. Little slide.
Okay.
Yeah, you would think so, yeah. All right, and this is always a fun one. That's a nice looking boat. Kind of the same situation. We reel in, okay, reeling in the boat, and so this is changing, and the dots are there just to kind of see that it's coming in at a constant rate. The rope is being pulled in at a constant rate. But you can see x is pretty slow. X prime is pretty slow in the beginning, but gets faster as you come in. But r prime would be a constant here. So there's another situation. That'd just be a Pythagorean theorem. Here's one that's going to be in your homework. A lamp and the shadow. You got a 15-foot lamp, 6-foot person. The black is the shadow. Now, what complicates this is you got a couple different things that are changing here. You have the green, so let's call that x, and they have an example in the book that you refer to when you're doing your homework. Let's call this x, so that would be x prime, the rate that the green changes, and what speed or rate would that be in this problem? How fast he's walking, right? So if he starts walking, I like his little walk here, right? So the green prime would be how fast he's walking. But at the same time, the black, call that S for shadow. The S would be the length of the black. That's also growing, right? So not only is X increasing, but S is increasing as well. And then you also have the tip of the shadow. The tip of the shadow is moving, and that is a combination of X and S added together, because you have the length of, you have the person walking, that's making the tip of the shadow move, and you also have the shadow growing. And so it's those two things put together. So again, that's a Pythagorean theorem kind of situation. All right, the one I want to look at here is this situation. We have a tank filling up with water, okay? And it's a cone-shaped tank. These are called conical tanks, and there are a lot of water tanks and so forth are shaped like this on, you know, farm grain things. There's conical shaped things like this. Now, let's take a look at this problem in this. Now, I've got two cone. I like the cone problems. Hint, hint, hint. Quiz Monday. The cone the cone, there's two different types. You've probably driven by, we drive around Shelton and that little curve on the other side of Shelton, and there's a big elevator there, and there's always, seems like there's always corn on the ground there. And it's always in this conical pile, what they call a conical pile, a cone-shaped pile. Okay? So sand's being poured on a beach, creating a cone, okay? And they'll talk about how fast is the height changing, how fast is the volume changing, how fast is the radiance changing of that. Or we could have the cone going this way, where we're putting water into it, or water's draining out. Same thing, okay? Or not the same thing, but similar. But I want to do this. So go ahead and draw yourself a cone on your paper here. Let's do this cone problem. At least get it, or a funnel. There you go, funnel. Mathematically, it's a cone, but we can call it a funnel.
But
All right?
it's all about applying math to the real world.
Real world, that's true. Why do we use special names in? I don't know. All right, so we have a funnel.
What does math make it so?
But funnels could be different shapes, right? They wouldn't have to be cone shaped.
What
I'm not sure I've ever seen a funnel that's something else. Well, it's square pyramid kind of funnel, maybe. I don't know. All right. Now, first of all, we are talking about, okay, this number right here is cubic meters. So that means what? That's volume. It's cubed. So that means volume. So what we need is a volume equation. Now, I will probably give you this on the quiz, although by the time we get to that point, you should all know it. You've done enough of it. A cone is just a third of a cylinder. So it's 1/3 pi r squared h is the volume of a cone. Okay? Now, there is a difficulty here. We could, and this number then is V prime. Okay, this would be V prime. So we're going to be doing a derivative of this. However, and as water fills, or as water drains from this cone, the water level is going to drop. So the radius is going to be changing, and the height of the water is going to be changing. Right? So these are both changing, so we can't plug any numbers into them yet. So we're going to be doing our derivative. Now we could do a derivative, and if we did a derivative of this, we'd have to do what? 1/3 pi is just constant, but we'd have to do a product rule, wouldn't we? Now that's going to make both an R prime and an H prime be in this problem. The difficulty in these cone problems is we usually do not have enough information to handle both of those. Now in the last problem, we had an X prime and a Y prime, and we were fine. And a lot of times that's true. But sometimes we do need to get it down to fewer variables. Now again, that's where you could confuse it with optimization. In optimization, we always had to get it down to one variable. But in this problem, these problems we usually don't. But in this problem, it turns out we do. Now, if you try to do a product rule, you will find out you still need more information. So I think in the cone problems especially, we're going to want to do this. Now, here's a special property that cones would have, a mathematical property. If I make this my water level here, okay, so this is all water in here. All right, here is the height of the water, that's H. And here is the radius of the water, that's R. Now, notice in the cone itself, I'll do that in red. Oops. This particular cone, got a little excited there. This particular cone is 16 meters high. So this cone is 16 meters high and a radius of 4. Now look at the blue triangle here and the red triangle. What do you notice?
They're similar.
Very good. Your geometry teachers will be very proud. They are similar, which means their sides are in proportion. All cone problems will need to use this proportionality idea. So, the radius to the height in this cone is 4 to 16. Now, I will tell you that some cone problems will be easier than that. Let me just drag up here, and I'll come back to this in a minute. The cone problem before this one said sand is poured on a beach, creating a cone whose radius is always twice its height. By them telling you that, that's really nice, because now I could just make a substitution. If the radius is always twice the height, I could just take out the R and put in 2H. And then I've got it down to one variable. So sometimes they give you information that makes it easy. In this one, they just told me the size of the tank. So I'm going to have to do this myself. So 4H is equal to 16R. Now you have to decide, do you want to solve for the H or the R? Well, it depends what they ask in the problem. In the problem, they want to know how fast is the water level falling. That's H prime, right? The water level is H. So I want H in my problem, not R. So I'm going to solve for R. So I divide by 16 and I get 1/4 H. So R is equal to, oops, that's not pi, that's H. Okay, so R is equal to 1/4 H. And then I'm going to substitute that in for the R. So this is something that you have to do in the cone problems, maybe some other problems, but mostly I want you to worry about it in the cone problems, that we do want to get it down into terms of just H. Usually it's just H, because we're usually interested in the height in the cone. And then you should simplify that. So 1/4 squared is 1/16 times a third, that's 1/48 pi, and then H squared times H is H cubed. You wouldn't want to leave it H squared times H, because then you got to do a product rule again. I mean, it's silly, but I've seen people do it over and over. They leave it like this. They do all the work and substitute, and then they leave it like this and try to do the derivative. Don't do that. Get it down to one variable, and like so. So H cubed. So here's where you're at. Now you're ready to go. See, now you can put in you can do your derivative, dv, dt, or your v prime. You'll end up with an h prime and an h in there, and you can plug your numbers in. So I won't finish this one, but it says, okay, when the tank is 12 meters high, or the water is 12 meters high, well, that'd be your h. Your h prime is what you're trying to find. And the v prime is the v prime in this one 2 or -2? Because water is draining out. So the volume is decreasing, so v prime would be negative. So, okay, and so h prime, your answer should end up being negative because the water level's dropping. Okay? But anyway, so you can see we went from kind of easiest to a little more difficult here, where we have a little more work to do to get it ready to go. Okay? All right. So for your homework here, we're going to do a little bit of both. We're going to do 3 problems. It's a little different than what the assignment sheet shows. Easy to say. So this is section 4.5. I can't remember the page number.
253 through 255.
253, okay. So starting on page 253, that'd be 4, 7, and 10. And those are going to be these rate problems. And then, oh, and by the way, number 3 in that sample 1 packet that we skipped is one of these problems. So at some point this week, you can go back and revisit that and maybe do it. Okay? So 4, 7, and 10 on that page, and then the business packet, try to finish the rest of that. And by the rest of it, I mean the circled one. 3 and 8, you notice were circled. So go through and try to get as much as you can of the rest of the business packet. Now, the answers are posted on the website, and I think you should try to get that much done. Now, we'll have time as we go through the week to be working on them, but we'll also have other problems that we'll be working on too. So to stay caught up and get practice, you should spend a fair amount of time in that business packet getting those optimization ones practiced. Okay? All right, rest of the time is yours. That's what you usually do, right?